Today I'd like to do a video about phase lock loops. For someone learning how to make a phase lock loop or learning about frequency modulation for radio and such, it was very hard for me to actually come up with a decent design to make everything by myself. I've read through 3 textbooks, and a lot of it is very theoretical, because in all honesty, it seems like most phase lock loops are actually just sold as packages nowadays. So not many people are crazy enough to actually make each component and put it together. But what's the fun in just buying something when you can make it? So for any other crazy people out there who are learning this stuff and actually want to try it, I'm going to make a video just pointing out some tips on how to actually piece by piece make it and put it together. So let's get into it. Let's go over quickly how a phase lock loop works. So what we have here is we have our RF signal. Let's say it's 40 megahertz, that comes into a phase detector. And also, what we have is we have our local oscillator that also comes into the phase detector. And what's important here is this phase detector is a fancy word, but it's just a mixer, okay? That is what made it very hard for me to understand how phase lock loop works, was this phase detector. It seems like some funky, crazy, advanced technology, but it's just a mixer. So what we do is we mix our RF signal and a local oscillator signal. And we're going to have both those signals be very close. Like we want them both to be 40 megahertz with a little give or take, because we can't perfectly tune them. And we take the output, which will give us both the sum and the difference of those two signals, and we pass it through a low-pass filter. We do not want the sum of the two mixed. We want the difference of the two signals, and we want the difference to be almost 0 hertz, or in other words, a DC signal. And we want to pass that through a low-pass filter and use it to change our voltage-controlled oscillator. And what we're going to do is that DC signal that comes through the low-pass filter is going to tell our voltage-controlled oscillator, our local oscillator, to either speed up or slow down. And if we're out of phase with the RF signal, the input signal, say we speed it up to get into phase. Say we're behind, we're minus pi over 2. We speed up our local oscillator so that it catches up and it tries to get close to 0. And then again, we run through this loop and say we sped up too much. Now we're plus pi over 8. So next time is we send a signal to slow the local oscillator down to go back, try to get closer to pi 0, 0 phase difference. And, you know, again, we overshoot. Now it's minus pi over 16. But we're getting closer and closer. And that's what this phase lock loop is we're locking in the phase through a loop. And we have an error signal that we're mixing with the RF signal to tell our local oscillator, a voltage-controlled oscillator, how much it needs to correct. And that how much it needs to correct will be the audio frequency that we're modulating in an FM radio. So we can actually take the output of the low-pass filter and amplify it and recreate the audio frequency that was modulated at, say, for example, the transmitter. That's what we're doing here. And the key thing to take away here is that our phase detector is just a mixer. That is really what stumped me in the whole process. First things first, here's our mixer. I hand wound a couple of tapped transformers. If you don't know what a tapped transformer is, look it up. I didn't know, but I figured it out. And what I did was I made a double balanced mixer. Here's a schematic for it. The printer kind of made it weird. In this case, it's a passive double balanced mixer. And that works just fine. Please look that up too on the internet. There's lots of better schematics for these kinds of things. Actually, there's even finished products. You don't have to go about and make one for yourself. You can just buy a double balanced passive mixer, and there's lots of good ones. But for me, what's the fun in that? You know, make it yourself. In our case right now, we have our local oscillator running at 38.57 megahertz and our RF signal operating at 38.57 megahertz. So we actually get a DC offset coming out from our mixer right here, and I can show you that real quick. It's a 327 millivolts is coming out of it. And that's the mixer part. So here is one of my voltage control oscillators. Here's the schematic for it. It's basically a Kurtz oscillator with an added varicap diode, where this is the voltage that is put across this diode changes the capacitance of the diode, and that allows us to modulate the frequency based on some input signal, which in this case is an input signal that's an audio signal, which we're amplifying through a simple op-amp configuration. And you see here, our Kurtz oscillator, there's no DC connection between these two. We have it tied in with a parallel capacitor. And this will allow us to change the frequency of our local oscillator. It also works perfectly as a transmitter too. So in our setup, I didn't go through and actually make I'm not actually transmitting and then receiving. I'm just have what is a transmitter connected directly to the mixer, so that we can skip the whole amplification, receiving and amplification steps. But if you actually want to do that, of course you could. So that's what we have here. We have one voltage controlled oscillator there, and it's connected to an audio signal that we're going to use to play some cool music. And then we have our other one that's going to mimic what would be our receiver's local oscillator. To finish off our components list, next we have that low-pass filter I was talking about. And this is simply a 47 ohm resistor in between our input and our output, and a 100 nanofarad capacitor grounding the output, or the other side of our resistor. And what this does is it takes the sum of the two frequencies are mixing and grounds that, so it doesn't pass through to our voltage controlled oscillator. And we end up getting a DC voltage to our voltage controlled oscillator, which is the error between the RF input and the local control, or the local oscillator's phase. And in our case, what that's going to be is it's actually going to be an audio signal, a very low frequency audio signal. And we also tap our voltage controlled oscillator correction voltage, the audio signal, and we're going to pass it through a preamp right here. And that's going to go to our speakers. Here is the output of our local oscillator and our RF transmitter oscillator. You see the yellow line is the RF, and the blue line is the local oscillator. You can see that they are the exact same frequency and more or less in phase. But when I say more or less, you see it's maybe negative pi/6 out of phase with the RF signal. And why does this occur, you might ask? This is because of asymmetries in the phase detector. When we made the transformers for the double balanced mixer, you may have made the lengths of the wire a little bit longer in one or a little bit shorter in the other. Those kind of asymmetries lead to differences in the phase. So you can actually correct for that by changing the wire lengths in your transformers. If you needed to have it more perfectly in phase, less of a phase error. But for our use right now, where we're doing audio modulation, audio demodulation, this is not going to cause us any trouble. So we're going to leave it as it is. Now I'm going to turn on some music that is connected to our RF oscillator, and we can listen to it. You can see even with the music going, it's still phase locked. There's a little bit of dancing going on. I think the volume might be too high, or tuning may be off a little bit. But if we try to change the tune, you can hear that and you can see that it goes out of phase. It's no longer phase locking for us, so we're not getting the proper audio signal back. But if we fix it, we can get it back into phase locking. Here we go. There we go. Now you see again, it's tuned, so it's able to correct itself and stay in lock with the RF. Pretty cool stuff. That's all I have for you. I hope you enjoyed my demonstration of how to make a phase lock loop out of common parts here and there. Everything I have in this demonstration is put together manually. Not the transistors, obviously, I didn't do that. And you can do it yourself, and I honestly suggest that you do it. It's quite fun to see it all come together and actually work, and took a lot of finicky business to get it to work actually stable. The biggest thing that was a challenge was making the voltage controlled oscillators so that they did not drift. And that's all about biasing. My suggestion is to read a book called RF Circuit Design by Bowick. There's a chapter about biasing transistors so that they don't change their capacitance and their behavior, their gain by temperature. And that's actually the best way to make really good stable voltage control oscillators, is to bias them correctly. And yeah, once you have a stable oscillators, it's actually quite simple. You just tune them and they work. So if anyone else wants to make it, please do. Have fun, and thanks for watching.